Okay, welcome to session number 8, topic 14, circuits. In the last session, number 7, we covered topics 13 and 15. Topic 13 covered electrical principles, and 14 or 15 rather covered the topic of good grounds. Um, Topic 14 is going to kind of wrap all this up, and it's hopefully you'll be able to grasp it okay. It's not really difficult. It's rather basic stuff. It's good stuff to know. And if you have your books ready, turn to page 146. If you'll notice on 146, there is a schematic diagram there. Let me get this started here. And this diagram kind of references the different symbols that are used to graphically represent the various components that make up um, the electronics within a circuit. This whole thing is a circuit diagram here. It's called a schematic, and we're going to identify these components just briefly before we actually get into the lesson material. So I kind of made a little bit bigger um, diagram here to follow. And if you'll notice here, couple of things. Um, why did this come out like that? In the book, it shows this component here as being flipped around. Trying to see here. Do 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 do. I believe this should be. I think it's correct in the book, if I understand this schematic properly. Pretty sure it's correct in the book, but not on the schematic diagram. So that should actually be flipped around. However, this whole diagram is what's called a Hartley oscillator. And this particular symbol right here is of a varactor. Um, and if you follow in your book the different symbols and everything that it lists here. Um, let's see, the symbol 11 is a variable potentiometer. Actually, potentiometer is, you don't have to put the word variable in front of it because potentiometers are variable. Number 8 is a bypass capacitor. And if you look at number 10, it blocks DC. That is a blocking capacitor so that only AC will pass if there is some there. Symbol 1 is a JFET. It's a transistor, a field effect transistor. And number 5 is a Zener diode. And the Zener diode helps to regulate voltage. Your DC voltage comes in. You also have a number 6, a transformer here. It's a amplifier output transistor, and then you have an NPN transistor as number 2 here. Symbol 9 is a fixed resistor. You can tell the difference. It's just a little squiggly line without this little arrow that you see here, but it is a fixed resistor. And symbol 3 is just a simple diode. So having identified these components here, we're going to get into the material starting on page 147 and see what kind of questions they're going to ask. As we go through these, follow along in your book. You'll see the different symbols that are graphically represented for each question, and also a picture of some components of what some of them actually look like. Might need a magnifying glass to see those, but oh well, that's the way it goes, I guess. All right, let's get going here on this. G7A09, symbol number 1 is the field effect transistor. The schematic symbol in the diagram is of an N-channel FET, and we know that because of the direction of the arrow that is there. being an N channel, this channel being the N channel or inwards is a good way to remember that, even though it is a bad pun. So, any rate, and you see the various types of field effect transistors there in the palm of that guy's hand. So symbol one is a field effect transistor. This schematic diagram might be in your test and just be able to really identify what the symbols are. Basically, is what you're going to try to do here. And you're probably only going to have a couple questions dealing with circuits. You probably won't have. I don't remember the exact number of questions that are going to be on the test for this particular topic, but you're not going to have that many. Yeah, I mean, you only have 35 total questions out of a pool of over 400 and some for the general class license exam. And even out of those 35 questions, you can still get 9 incorrect and still pass and get your general ticket. So, don't overthink this, um, and don't be overly concerned about the questions. But it's good to know what these symbols are and to kind of lock them away in your mind and be able to identify circuits and the various components. Symbol 5 is the Zener diode used for voltage regulation. The Zener diode helps to it will conduct voltage in one direction, current in one direction, I should say, until it reaches a certain saturation point, and then it goes backwards. So you see the cathode end of the Zener symbol is somewhat of a Z-shaped, and that kind of gives you an idea of if you see that little um, Z-shaped line there, you know automatically it's going to be a Zener diode. So remember that in nearly every case, a Zener diode is in the circuit backwards from a normal diode. And like I say, when it helps to protect certain things within your equipment, and that when it reaches a certain saturation point, it will conduct in the opposite direction. Zener diodes are often used in crowbar circuits. Again, it helps to protect certain without blowing the fuse necessarily. So when you see the symbol that's shown here, symbol 2 is an NPN, negative, positive, negative junction transistor, NPN. And the arrow always points to the N. So as soon as you see that arrow, you know that this is going to be an N part of the transistor. This is going to be the positive, and the other side is going to be the negative. Okay. So you have the collector and the emitter and the base on here. Base, collector, emitter. All right. Did I? Okay. Yeah, I'm on the. Okay, it's easy to spot what a transformer looks like, and we see that as symbol 6. So the two vertical lines indicate an iron core. Sometimes you'll see a dot near the ends of the windings, and the dots usually indicate the relative phasing of the transformer. This is more common in radio frequency transformers, such as balance and transmission line transformers. Um, but that is what your typical transformer is going to look like. To make sure your core or dielectric in there between the primary and the secondary um, kind of gives you an idea of what kind of transformer it might be. Now, this is actually what tells us that this is a Hartley oscillator, and that's symbol number 7. This is just one indicator. It is a tapped inductor, and what you see there is a bunch of different taps going to different components and everything. It provides the necessary feedback to keep the oscillator oscillating. So the tapped inductor actually functions as a step up auto transformer. Now, you'll also kind of see this type of tapping inside of an antenna tuner. Some of your MFJ antenna tuners, instead of having a smooth roller inductors and capacitors and everything that just are variable tuned, they'll have actually switched number indicators on the front panel. And what those are doing, they're actually switching these particular wires in and out at particular points along that coil. If we have three equal value resistors in parallel, now if you go back a little bit to your electrical principles, particularly back when you got your technician class license and took that, you'll understand a little bit about how the individual how resistors work in parallel. So you'll have three individual paths for current flow, and in parallel, it decreases the ohmic value by 1/3 if you have three of them in parallel, 1/4 if you have four of them, et cetera, et cetera. But it's pretty easy to kind of figure this out in your head, okay? 1/3 the resistance of each 100 ohm resistor is 33.3 ohms. This is going to be an easy question, folks. So you're really not going to have to do any real number crunching or heavy calculations to figure this out. But if you take out three 100 ohm resistors, your approximate total resistance in ohms across all three of those in parallel is going to be 33.3 ohms. Heating a resistor always decreases its resistance, and the amount of change for any particular temperature change depends on the resistor's temperature coefficient, which depends on the materials used in the resistor's construction. If you heat a resistor too much, and as like it says here, you decrease the resistance in that, you can almost effectively just blow the resistor totally. But what you're doing is that you're allowing way too much current to flow in that particular circuit. If that resistor's capability, rated capability, is breaking down. So you got to be very careful about that. If you if you go into a circuit and replace a resistor, you need to replace like components with like components. So you wouldn't want to take and put a half watt resistor, or you wouldn't want to take a bad half watt resistor out and replace it with a quarter watt resistor. That just wouldn't work. It wouldn't work very well, and it wouldn't work very long. So you want to make sure that you do the proper wattage of resistor and the proper value if one goes bad. If you add up the current in each branch of a parallel circuit, you will come up with the total current in a circuit. You got to think about this a little bit. Current does divide, and if you have a certain amount of current going into several branches of the circuitry, the current that goes in, it has to really equal the current on the output. So that's one thing to kind of keep in mind. On page 148, there's a little Elmer point there about electrical circuits, and make sure you read that at some point, and also peruse the schematic symbols down below on that page as well. Kind of gives you an idea of what some of your logic circuits are, your amplifier circuits, and various other components that you're going to find in your radio. Do, 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 do. Where are we? G5B02. Okay. So the next one has to deal with three resistors in series. So these same there's The three resistors are of the same value, 450 ohms. And so there's going to be a total resistance there that uh, you're going to calculate. So if you have three same value resistors in series whose total resistance adds up to 450 ohms, each resistor will have a value of one third of that 450 ohms. So 450 divided by 3 is going to equal 150 ohms. And yeah, check your answer there. That's fine. Just know that when you have those in series, it doesn't matter if you have three 100 ohm resistors in series, they're going to add up to 300 ohms. And they can be different values as well. I mean, you might have a 100 ohm, a 200 ohm, and maybe a 150 ohm. So when you add up those three together in series, the 100 and 200 is 300, then another 150 is again 450 ohms. So they can be different values. You just got to remember that there's a total resistance across all the resistors if they're in series. So while you can solve this particular problem there in G, let's see, which one is it? G5C15 is asking you the total resistance of a 10 ohm, 20 ohm, and 50 ohm resistor connected in parallel. The formula is very simple here. And if you want the total resistance, if you look at that formula, you're going to take and you're going to divide the reciprocal of each value is going and then you're going to add those together and you're going to come up with the total resistance. So the 10 ohm resistor, let's say that's R1, you're going to divide that into 1. You're going to take the 20 ohm resistor and you're going to divide that into 1. You're going to take the 30 ohm resistor and you're going to divide that into 1. You're going to add all these together and you're going to come up with 5.9 ohms predominantly is what they're saying here. So the thing to remember about this is that the total uh, amount of ohms represented in a circuit like this, in a parallel, this they're talking about a parallel circuit, not a series. We just covered that series. We're talking about a parallel. It's always going to be less than the smallest value component. So when you see that 10, 20, and 30, you automatically know that whatever you work out is going to be less than 10 ohms. So just kind of a rule of thumb to kind of keep in mind there. But that is the formula for figuring out total resistance in a parallel resistance circuit. So here's another easy one right here in this particular one. That's what this says. Um, oh, by the way, on the bottom of page 150, there is a color code to resistors, and it's important to know that color code and how to interpret it and read it if you really want to get serious into electrical circuits and electronics and things of that sort. So, in this particular question here that we have up, G5C03 is asking about the following components, which one should be added to an existing resistor to increase the resistance. Okay. So to add more resistance to a circuit, you simply add a resistor in series. Okay. Remember that. We're bouncing around here. I understand that. But, we've talked about series resistors, parallel resistors, and now again, we're talking about a series configuration in which you add resistors in series to add more resistance to a circuit if necessary. Let's say, for instance, you had a 450 ohm resistor, it's a half watt resistor that got burnt out in a circuit. Well, you don't have a 450 ohm resistor. However, you do have maybe a 200 ohm resistor and maybe a 250 ohm resistor. You can put those two in series as long as they're still half watt resistors. Put those in series to come up with 450 ohms. Capacitors are a little bit different. Capacitors in parallel add up, similar to resistors in series. So if you have a certain amount of capacitance per capacitor and they're in parallel, you're going to add those values up the same way you would add the values of resistors in series. So C1 plus C2 plus C3 equals total capacitance. Um, One thing to note is that in this particular question, they've mixed one capacitor that's a picofarad capacitor with two same size nanofarad capacitors. But it's not as difficult as you think. So you take a look at the 750 picofarad capacitor and determine what its value is as a matching nanofarad capacitor. And to understand this is to understand the difference between pico or pico, some people pronounce it either way, and the difference between a nano value. So to convert the picofarad to the equivalent nanofarad, and again, nano is a little bit smaller, not a little bit, nano is smaller than a picofarad. And if you're a Star Trek fan or anything like that, you know that maybe an episode that Wesley Crusher on Next Generation was experimenting with nanites, and they got away. They were extremely small. You can't see them. They're so small. Just know that pico is larger than nano. So you move the decimal point 3 places to the left. The 750 picofarad capacitor is now equal to 0.750 nanofarads. So now you can do easily the math of the 3 capacitors by that are in parallel simply by adding the 5 pico, the 5 pico, or I mean the 5 nano and the 5 nano plus the 0.750 now nano. You come up with 10.750 farads. Here's a little handy hint that is included in this question. In a test, you can encounter mixed units as in this question, such as milliwatts and microwatts. If working with metric prefixes isn't second nature, always convert the values to their fundamental units first. So, in other words, rewrite the numbers as watts or ohms or farads, not nanofarads or picofarads, so that when you're all done with the calculations, you can go back and give the answer in the units that are being asked in the question. And you can save yourself a lot of heartburn by doing that. So, understanding the quantity of these particular metric prefixes represent will help you understand how far you're going to move those decimal places, whether it's going to be 3 or 6 or whatever, and which direction you're going to go with it as well. All right, we have 3 like capacitors in series, and since they are in series, just like resistors in parallel, the total capacitance will be 1/3 of each of the 100 microfarad capacitors. In other words, these are in series, and the calculation is done very much like you would do the calculation for resistors in parallel. You just got to think a little bit of the opposite there. So if they're 100 microfarads, you're going to take the reciprocal of each one of those. You're going to come up with 33.3 microfarads as your answer. Calculating for total capacitance of unlike capacitors in series is a little bit much like the formula for calculating unlike resistors in parallel. Again, you have C1 times C2 divided by C1 plus C2. So in this equation, the total capacitance will always be less, again, like in the resistor, it'll be less than the smaller capacitor. So 14.3 microfarads can be confirmed as the correct answer by working through the formula shown here. We're on G5C17. Make sure I'm on the right page here, and that's on page 152. So we're looking for a value of nanofarads of a 22,000 picofarads capacitor. So metric prefixes come in groups of 3 decimal places. starting 3 places to the right of the decimal point. We have milli, micro, nano, and pico, or thousandths, millionths, billionths, and trillionths, respectively. That's what all those represent. So there are 1,000 picos in a nano. Dang, did I get that wrong? I'm backwards. Pico is smaller than nano. My apologies on that. I don't know what I was thinking here. Um, so 22,000 picofarads divided by 1,000 equals 22 nanofarads, or 22 NF. And please forgive me for kind of messing that up. I get a brain fart once in a while. But at any rate, so as minuscule as a picofarad may seem, it's a very common unit in radio work. Just remember that. You're going to see most of your capacitors in picofarads. So each metric prefix represents 1,000 to 1 ratio of the prefix next door. We have 1,000 millis to a single unit, 1,000 micros to a milli, 1,000 nanos to a micro, and 1,000 picos to a nano. Since there is a 1,000 to 1 ratio between nanos and micros, we can divide 4,700 nanofarads by 1,000 to come up with 4.7 microfarads. So that's another common one you're going to see. You're going to see the pico and the microfarads. Seltzer water, folks. Sparkling water, I should say, not seltzer water. Always remember the smaller unit. The more of them you need, hence the larger the answer, and vice versa. If we need to add some additional capacitance to a circuit, which already has a fixed capacitor, we would add a second capacitor in parallel. Okay, remember, if you need more resistance, you add that in series. If you need more capacitance, you add it in parallel. If we need to increase the inductance of a circuit, we would simply add another inductor in series. Remember, an inductor is much like a resistor. It's measured in a little bit similar way that a resistor is done. And so inductance in series, much like a resistor, it will increase the amount of total inductance in that circuit. One thing to do is to treat inductors like resistors, is what I was just saying, when working either a series or a parallel problem. So this one's pretty easy. You can do in your head. So you got three 10 millihenry inductors in parallel. Think again, resistors in parallel. So the total inductance will be about a third of, and they're all the same value. They're going to be around a third of what your total inductance in with 3.3 millihenries. Daggone it. Got this stupid tickle in my throat. I wanted to cough. So, at any rate, let me repeat that. The total inductance will be 1/3 or 3.3 millihenries when connected in parallel. These are open air coils, and they're mounted on a circuit board held in place by some blobs of hot glue to retain their precise inductance. If you were to go in and kind of spread those apart, it will change the inductance of that coil. So typically, what the manufacturer does is they put them in place so that, um, and they have them put in that way for the precise inductance that is needed for that particular circuit. So don't go spreading those things apart if you're kind of digging around inside your radio. You could change a few things, and that's not always a good thing. So here's an easy one for this particular question. So they're talking about the inductance of a 20 millihenry inductor connected in series with a 50 millihenry inductor. And again, you add this up just like you would a resistor. 20 plus 50 is equal to 70 millihenries. Inductive reactance is the opposition to AC, which is caused by the inductors. Capacitive reactance is the opposition to AC caused by capacitors. Um, so you have two different types of reactance. You have inductive reactance and capacitive reactance. But both of these reactances vary with frequency. When there are an inductor and a capacitor in the same circuit, there is a special frequency, which is called the resonant frequency, where the inductive reactance equals the capacitive reactance. Now, these can be configured in different ways, and this is why you have, the balance that are on your antennas basically are kind of like a capacitive and inductive reactive components. Um, if you look at a tri-band beam, for instance, and you'll notice these little cans that are on the elements that make up a beam. Um, they're tuned circuits, which means that when you transmit on a particular frequency, that those cans are tuned in such a way that they will block all frequencies or band, or I should say, except what it's allowed to pass. So when it is resonant, it will pass the frequency that you're tuned into. So just something to kind of keep in mind. Here we have a schematic of what a tuned circuit or a resonant frequency circuit might look like. And these are some of the formulas to determine that. If you know the inductive reactance of the coil and the capacitive reactance of the capacitor, you can uh, calculate what the frequency is for that particular circuit and what it will pass. Let's say this is tuned for the frequency band of 20 meters. So it's going to pass. Um, it'll block other frequencies, but pass the uh, frequency that you need for 20 meters if it's a resonant circuit for 20 meters. Any rate, you think of an inductor as a coil of wire. Its opposition to AC is called inductive reactance, which is calculated as XL, which is equal to 2 pi frequency inductance, okay, where F is the frequency in hertz and L is the inductance in henries. X um, Inductive reactance increases as frequency increases, by the way. Remember, coils are inductive, capacitors are capacitive. The ohm is the unit of measurement for reactance as well as resistance, by the way. A capacitor has plates separated by an insulating dielectric, and its opposition to AC is called capacitive reactance, which is calculated as capacitive reactance, or XC, is equal to 1 divided by 2 pi FC. Again, where F is the frequency in hertz, remember that, in hertz, and capacitance is the capacitance in farads. So if you're working this formula with kilohertz or megahertz, you want to convert that to hertz. And if the capacitance is in microfarads or picofarads or even nanofarads, um, you need to convert that to farads in order to work this formula. And remember, while um, inductive reactance increases as frequency increases, capacitive reactance actually decreases as frequency increases. Again, oops, I'm going the wrong way here. I want to go back to this one here. Inductive reactance increases as frequency increases. Capacitive reactance decreases as frequency increases. Capacitors offer reactance to AC inversely proportional to the frequency, and that's why it decreases as the frequency increases. So capacitors have high reactance at low frequencies and low reactance at high frequencies. And if you remember, as F increases, capacitive reactance decreases, and there is your formula once again. Inductors are coils and they are effective in reducing alternator wind and high frequency mobile installations. The higher the alternator wind frequency, the greater the reactance from the inductor. So remember, as frequency increases, inductive reactance also increases. Again, there's your formula. Just reiterating and repeating the same thing over again just to make sure that there is a good understanding of how capacitive reactance and inductive reactance, how they work as it relates to frequency, whether frequency increases or decreases. The term impedance means the opposition to the flow of alternating current in a circuit. So impedance to AC can be made up of resistance only, reactance only, or both resistance and reactance. And you can create impedance to AC by winding a wire around a pencil to create a coil. And this is called a choke. And this little handy choke might minimize the alternator wind that may come in on your new worldwide mobile high frequency station, which is temporarily mounted in your vehicle. Or maybe not. Maybe it's permanently in there. But at any rate, a choke is a good thing to have. Excuse me. Good thing to have or to make if you want to reduce a little bit of alternator wind. Again, the ohm is also used for measuring impedance. Thus, the ohm may mean impedance, reactance, or resistance. Those three are all measured in ohms. Two AC circuits might be impedance matched by using coils and capacitors between the two circuits. This is known as an LC circuit. When impedances are matched, we have the greatest amount of power transfer. An impedance matching transformer allows us to precisely match radio stages for the maximum transfer of power. So you don't want an impedance mismatch. This is what happens on your antennas. It's looking, your radio output is actually looking for a nominal uh, resistance, reactance, impedance. Impedance is more proper of 50 ohms going out to the antenna. And if your antenna is mistuned, the resulting mismatch in the circuit will cause a higher impedance that your transmitter is not going to like. And that's why antenna tuners were invented, so that you can actually match that impedance as closely as possible to 50 ohms. And it still may not be a very efficient antenna system, but your radio transmitter is going to be much more happy about it anyway, and it doesn't care. So there you go. So an impedance matching transformer allows us to precisely match radio stages for the maximum transfer of power. And this is all has to do with internal stuff. And remember the NFL principles of transformers, no free lunch. While a properly matched transformer can minimize losses, you never get any more power out of it than you put into it. The product of voltage and current on the output can never be more than the product of voltage and current on the input. So if you step up the voltage, the current must go down and vice versa. Do, 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 do. Okay. Give me just a moment here. Okay. In order to transmit maximum power from a source, such as a transmitter, to a load, or such as an antenna, your antenna being the load, there must be an impedance match. And this means that the internal resistance of the transmitter and the antenna resistance need to be the same, typically 50 ohms, as well as I was just explaining to you. So, and that applies more to the modern ham radio that you have out there these days. However, you need to remember that impedance is not just a simple resistance, but also includes any reactance, which we can't just ignore. I mean, we need to take in reactance as part of the equation as well. But the simplest solution is to operate on the antenna's resonant frequency, in which case the reactance is zero. So if you, we'll get into a little bit more of HF antennas, I believe, at another time. But if you remember back from your tech class, a little bit about this, how to calculate the resonant frequency of an antenna. If you're doing just a wire antenna dipole, a simple little dipole, you're going to calculate using the formula you need to calculate for the length of that antenna based on the frequency or range of frequencies you want to operate. Um, a lot of times, what you'll find when you buy commercial antennas, or even when somebody provides a simple design for an antenna, they will almost always include a chart which shows where supposedly where the resonant frequency is of that antenna. This is the central uh, part of the antenna. And now you can actually operate over a little bit broader spectrum on that same antenna, but it'll show you the SWR curve, and also it'll give you a little bit of an impedance indication as well, as it shows that SWR curve go up on the edges. You never ever really want to run anything greater than a 2-to-1 SWR on your transmitter, because that usually indicates anything over that as a fairly hefty impedance mismatch. And to be on the safe side, operate under 2-to-1, even better, 1.5-to-1. You'll never get a perfect 1-to-1 match. You'll usually get a 1.1 or 1.2 for the central frequency that an antenna is cut to, or a resonant frequency of a tuned circuit. But at any rate, when source and load impedances are matched, you will be able to get maximum power out to the load. In this case, the load is the antenna. And most of your modern HF radios have a built-in capability to reduce power on the output when there is a significant impedance mismatch going out to the antenna. That helps protect your finals. And final transistors and tubes are not very cheap these days. There are plenty of ways you can match impedances at radio frequencies. At the antenna, we sometimes use fractional wavelength impedance matching transmission lines. In a radio RF output stage, we might use an impedance matching pi network. And within the radio, small transformers will allow us to also do impedance matching. So, all of these are great ways for providing the maximum transfer of radio frequency energy. You look at any type of modern receiver within that band selection and that particular part of the circuitry that controls that particular band, you'll see a whole slew of tuned circuits in there. Always make sure your general class worldwide antenna systems have an impedance of around 50 ohms for maximum power transfer. Some of the transceivers will have a built-in automatic impedance matching antenna tuner, like much like my TS940S Kenwood. It has an internal tuner so that, and also the meter has an SWR meter. But what you do is what I can do here is I can hook that radio directly up to an antenna. And I actually want to have that antenna as close to the band operating frequencies as possible that I intend to be operating on. And that way it's a little bit easier and a little bit quicker on the tuner. But what happens is that you push a couple little buttons and you hit the key, you key the transmitter, and you hear this little whirring inside the radio, and you watch your little needle on the meter on the front of the radio. And when it finds the resonant frequency internally to match that antenna, then it's going to give you maximum transfer of power out from the radio through that tuner section. And it doesn't necessarily mean the antenna is going to be efficient, but you're actually going to still transmit something out there. As discussed earlier, impedances should always be the same for maximum transfer of power. Again, this is at referring to the 50 ohms. So therefore, you want the low pass filter to have the same impedance as both the transmission line and the ham transceiver to which it is connected. When it's talking about a low pass filter here, it's talking about something to help minimize interference, say on your TV transmitter or TV or radio receiver that might be sitting in the living room or the kitchen or maybe your neighbor's house or something. That low pass filter is only going to pass the frequencies necessary for you to operate your ham transceiver. And it's a rather broad low pass filter. So you don't have to worry about losing too much power with those if that's a concern. If you're able to scrape off the brown glaze coating on a wire wound resistor, you would quickly see it looks exactly like a coil with evenly spaced turns. Actually, it is an inductor and would not be suitable in any circuit that could accidentally make the circuit performance unpredictable through the use of the wrong components. So normally we do not. Normally we find the wound resistors just in simple DC applications where we just need a drop a small amount of voltage with relatively high current being passed. Why these are wire wound resistors. All right, the ceramic capacitor is the workhorse in ham radio equipment. Their reliability is very good and their comparatively low cost helps to keep radio equipment reasonably priced. So remember that ceramic capacitors, an advantage that it has is comparatively low cost. When you pass the exam and earn your general class privileges, you may begin to operate HF. Remember that when you do that, you give your call sign if you're operating on those general class privilege bands. You give your call sign that was assigned to you as a tech, followed by the /AG. and that lets people, other hams, know on the air that if you're operating on there, they happen to look you up on QRZ, and they see in QRZ that you're only a tech class licensee. If you don't have that AG on there, they may not talk to you. So be sure to have that AG appended when you're talking on the HF bands or other bands where you have general class privileges at that point. So a couple of rigs actually have their batteries on the inside. With any portable transceiver, including VHF, UHF handhelds, make sure they never get dropped. Dropping radio equipment can fracture the brittle iron cores within a toroidal inductor. The ferrite core within a toroidal inductor offers large values of inductance, with most of the magnetic field contained within the core, so it does not affect other nearby components. If you looked inside a radio and you see these little cans, okay, some of them are they have a little adjustment uh, that you can see there. Those are coils, and that is a ferrite core, and that helps to keep the magnetic fields away from other components that can affect the operation of your rig. The toroidal inductor may be used in applications where core saturation is desirable. So, as far as this question is concerned, all the answer choices are correct in this one. G6A18. Solenoid inductors will interact if they are placed side by side due to mutual inductance. To minimize this, two solenoid inductors should be placed at right angles to their winding axis, and that way you will minimize unwanted mutual inductance. Just kind of think about how a transformer winding favors mutual inductance, but placing them at right angles will minimize the effect. Think of a transformer with interlaced coils through mutual inductance within the transformer. So voltage is applied to the primary and it will also appear across the secondary. And this is mutual inductance. Typically, you either have a step up or a step down transformer. If you put a voltage into, say, a step down transformer that's 110 volts, 120 volt input on the primary, and you have mutual inductance, you have windings that are in the same interlaced form that the primary is. That secondary is smaller, however, it may be 16 volts output as a step down transformer. But what is happening in there is that there's a mutual inductance occurring. On any ideal transformer, the product of the primary voltage and current has to equal the product of the secondary voltage and current. Read that again. On any ideal transformer, the product of the primary voltage and current has to equal the product of the secondary voltage and current. In other words, this is one of those no free lunch principles of transformers. You can't get any more power out than you put in. A step up transformer will have low voltage, high current on the primary side, and high voltage, low current on the secondary side. Conversely, if you have a step down transformer, you will have a high voltage and low current on the primary side, and you'll have a low voltage and a high current capability on the secondary side. So the primary winding needs to have larger wire to handle the higher current if it is a low voltage, high current step up transformer. So in this particular question, it is a turns ratio problem, and it is relatively easy to solve by using the equation shown here. It simply means the voltage of the secondary is equal to the voltage of the primary times the number of turns of the secondary divided by the number of turns of the primary. So it's derived from the equation that says that the ratio of the secondary voltage, which is represented by ES. E, of course, voltage, S is the secondary, to the primary voltage, represented again, E voltage, P primary, is equal to the ratio of the turns on the secondary, which is NS, okay, to the turns on the primary, which is shown as NP. So again, secondary voltage divided by primary voltage is equal to uh, secondary to the secondary N to the primary N. So multiply 120 times 500. And the ratio here being 500, of course, and represented by secondary N. And then divide your answer by 2250. And this gives you about 26.7 volts. Your calculator keystrokes are as follows. And that gives you the answer of 26.7 volts. So those are the ratios. N is the ratio of turns on the secondary and primary. Boy, oh boy, we got a lot of reading here. Again, a transformer always consists of two or more windings of wire that are magnetically coupled. The ratio of voltages of transformers is proportional to the turns ratio. A transformer with 10 turns on the primary side and 100 turns on the secondary side is a 10 to 1 step up transformer. Likewise, a transformer in this question with the 400 turns on the primary and 100 turns on the secondary is a 4 to 1 step down transformer. Whatever voltage you put across the primary winding will be divided by 4 on the secondary. Going back through the transformer the other way, the input voltage is multiplied by 4. So that's an important thing to note. While a transformer can have a tremendous amount of voltage step up, again, there's no free lunch. It has to have a low current. The power out of any transformer is only equal to the power going into the transformer. And of course, there's going to be a few losses. So if you have a 4 to 1 voltage step down transformer, uh, if again, um, a 4 to 1 voltage step down transformer will have a 4 to 1 current step up. And the product of the input voltage and current must always equal the product of the output voltage and current. There you go. Oh boy, this equation, the equation that applies is ratio of turns on the primary divided by the ratio of turns on the secondary is equal to your impedance of the primary divided by the impedance of the secondary. And as this states here, you're getting into square roots and a few other things, but it, I don't even know why they even put this in here because this actually kind of, in my opinion, just kind of confuses things. So let's just go ahead and skip on down a little bit here to the bottom. If you find the square root of 150, you know that a square root multiplied by itself gives you the number you want. So you can do it simply by approximation. Since 12 by 12 or 12 times 12 is 144, 13 times 13 is 169, you know that the square root of 150 is going to be between 12 and 13. So the only answer given that is close to this is 12.2. And if you choose that, you will have the correct answer. And you don't have to remember how to do square roots. The calculator keystrokes are 600 divided by 4 equals 150, and then you press the square root key to produce the answer of 12.25. So you really don't have to do the square root itself, but it is part of the equation. Just kind of remember that. All right, we've kind of come to the end here to get into the Q&A section. This will be the only topic we're going to cover tonight. Um, and that'll wrap up this session. The next session we're going to talk about is going to actually cover HF antennas. Um, that is 112 slides long, so it might be rather intense, and we'll see how it goes in that session to decide whether we're going to split that between two sessions or not, because we only have three topics to cover after this evening. We got topics 16, 17, and 18. Topic 16 again is HF antennas. Then we're going to talk about topic 17 of coax cable. And then the last topic is RF and electrical safety. And both of those topics, topics 17 and 18, are about 50, 51, and 56 slides long. They'll be short. What I'd like to do, if we can wrap up HF antennas in the next session, session 9, and get all 112 of those slides in for a single session, that'll leave us with Thursday and Monday to cover the last two topics, along with Tuesday doing a quick review of a few things that need to be covered or anyone wants to cover. Any rate, let's get back to this topic here of circuits, and we'll get into the Q&A here. Going right back to the beginning of that of this topic, we see that little okay, sorry about that. We see that little schematic diagram there, and which symbol in figure G7-1 represents a field effect transistor. And we know that this one right here is the field effect transistor. Symbol 1, your answer is going to be C. Your Zener diode. Remember that little squiggly line that looks a little bit like a Z is going to give you a clue as to what the Zener diode symbol actually looks like. So it's symbol 5, or your answer is D. Which symbol represents stand by. All right. Next question here. I don't know why. I just need to turn off my phones when I get in here, and I don't remember to do that. My apologies. So, which symbol represents the NPN junction transistor? We see in the schematic here, there's your NPN transistor, symbol 2. Your answer is going to be B. Which of the symbols represents a multiple winding transformer? Pretty easy stuff. We just really finished up doing that. Symbol number 6, or your answer is C. Which symbol in the figure represents a tapped inductor? Remember, we're talking about an inductor here. We're not talking about a potentiometer, but we're actually talking about an inductor. So if you can figure that out, it's pretty easy. So you have that's your potentiometer there. That's your tapped inductor right there. Symbol 7, and your answer is A. So what is the total resistance of three 100 ohm resistors in parallel? And remember that when you have multiple resistors in parallel of different values, your total resistance is going to be lower than the smallest value resistor. So these being in parallel and they're all the same, 100, it's pretty easy if you divide 100 by 3 and you come up with 33.3 ohms. What will happen to the resistance if the temperature of a resistor is increased? the temperature of the resistor is increased. And you got to remember that it will change depending on the resistor's temperature coefficient, or C. Typically, when the temperature of a resistor is increased, the resistance of the resistor decreases. But it really depends on the temperature coefficient of that particular resistor. How does the total current relate to the individual currents in each branch of a purely resistive parallel circuit? Remember, whatever current goes in has to equal the current going out, but it equals the sum of the currents going through each branch. So if you have, let's say you have 99 amps going into the circuit, and you have, let's make it a little bit simpler. If you have 50 amps going into a circuit, a parallel circuit of resistors, that 50 amps is going to be divided across those branches, so that you might have 25 amps going into one, depending again on the resistance of that of one branch. You might have 15 amps going into another, and you might have 10 amps going in, into another branch, but they're going to be the same on the output as well. They're going to come back together and again be 50 amps. So it equals the sum of the currents going through each branch. If three equal value resistors in series produce 450 ohms, what is the value of each resistor? This is a very simple, these are equal value resistors. You got to remember there's three of them. They're all equal value, and the total in series is 450 ohms. You just divide that by three, and you come up with 150 ohms for each resistor. What is the total resistance of a 10 ohm and a 20 ohm and a 50 ohm resistor in parallel? This is very simple. Again, when you look at this, uh, if they're in parallel, okay, the total resistance is going to be less than the lowest value. Your lowest value resistance here is 10 ohms. So looking at this, you can almost you don't wanna do 0.17 ohms, but it's gonna be closer to 5.9 ohms is what you want. So this is a rather easy one just to look at and just automatically know that, there's gonna be some value, and it's gonna be greater with common sense, gonna be greater than 0.17 ohms, so 5.9 is really the logical answer on this question. So, which of the following components should be added to an existing resistor to increase the resistance? You need to add components to add to an existing resistor to increase the resistance. Remember what happens when you uh, add resistors in parallel versus adding resistors in series. And we're talking about resistors here, not capacitors. So the last two answer selections in this are definitely incorrect. But if you want to add resistance, you put them in series. Your answer is B. What is the equivalent capacitance of two 5 nanofarad capacitors and one 750 picofarad capacitors connected in parallel? Remember what happens when you uh, have capacitors in parallel, unlike resistors that are in parallel. Uh, Capacitors in parallel are like resistors in series. You're going to add those values together, and you're going to come up with, since you have five, you're going to change your value here, so that when you move the decimal places of 750 picofarads over three places, you're going to come up with a 0.750 nanofarad. So your total capacitance is going to be 10.750 nanofarads. What is the capacitance of three 100 microfarad capacitors connected in series? Now, just like resistors in parallel, you're going to use the same kind of formula for capacitors in series. They're going to be less than the total capacitance that's represented there. So if you have three 100 microfarad capacitors, um, then you're going to divide that by 3, and you can come up with about 33.3 microfarads. The capacitance of 20 microfarad capacitor in series with a 50 microfarad capacitors. Remember what happens with that series, okay? And you've got to remember again that capacitors in series are like resistors in parallel. You're going to decrease the capacitance in series that way, and it's always going to be less than the lowest value capacitor that you have. When you look at this, your lowest value capacitor is 20 microfarads, and common sense will tell you that's not going to necessarily be 0.07. So the only logical answer here is B, 14.3 microfarads. The value in nanofarads of a 22,000 picofarad capacitor. Okay, you remember your pico is a different value altogether. Okay, it's a smaller unit. You need to make sure that you move your decimal places the proper number of spots. So if you have 22,000 picofarads and you're going to move the decimal point from here over to here to get 22 nanofarads. Alrighty. What is the value in microfarads of a 4700 nanofarad capacitor? And if you remember that you're going to, again, you're going to move your decimal places. Since nanofarads are smaller than microfarads, you're going to move that decimal place from here to there to come up with 4.7 microfarads. That's a little symbol for micro, by the way, when it comes to capacitance. So 4.7 microfarads is the correct answer, D. Which of the following components should be added to a capacitor to increase the capacitance? Remember, and we're talking about capacitors here. We're not talking about inductors or resistors. So the only two answers you have to choose from are C and D. But what happens if you want to add capacitance? You want to increase that capacitance. Acts different than resistors. Resistors in series, you can add resistance in series to add resistance in that circuit. But when it comes to capacitors, it's just the opposite. You add a capacitor in parallel. Which of the following components should be added to an inductor to increase the inductance? Um, we're looking at only two possible answers here again, C and D. If we're talking about an inductor, you can automatically dismiss A and B because they talk about capacitors and resistors. So which one of these choices of C and D are we looking at? Remember that inductance is again measured in ohms, and it acts very much like a resistor in series. So if you're adding resistors to add resistance, add a resistor in series, you're going to do the same thing with an inductor. You're going to add it in series. So, what is the inductance of three 10 millihenry inductors connected in parallel? Much like the resistors, you're going to divide that down. The total resistance is going to be less than the three of them combined in series. So, if they are in parallel, you automatically know, and again, it's millihenry. Keep an eye on this. We're talking about millihenry here, so automatically we can kind of dismiss A and B out of this. Uh, but we also know that it's going to be less than the smallest value. In this case, they're all the same, but it's going to be less than 10. So the only logical answer in this is going to be 3.3 millihenries, or you're going to divide 10 by 3. So the inductance of a 20 millihenry inductor in series with a 50 millihenry inductor, we kind of again, it's like resistance. You're going to add these together. 20 plus 50 is going to give you again 70 millihenries. They're both the same value, so you don't have to change anything, but you just have to be careful. Just 20 and 50 is 70. This is an easy answer. What is reactance? Okay. Be careful with this one because, again, reactance is much like resistance. Okay. If you look at A there, it says the opposition to the flow of direct current caused by resistance. We're not talking about direct current. Reactance is something totally different, and it's actually operating with alternating current. It's if you remember alternating current as the main component here, uh, to apply reactance to, it's going to be the opposition of flow of alternating current caused by either capacitance or inductance. Remember, you have the capacitive reactance and the inductive reactance. So, which of the following causes opposition to the flow of alternating current in an inductor? Uh, which of the following causes opposition to the flow of alternating current in an inductor? Very simple answer here. Again, we're talking about alternating current. And when we're talking about alternating current and opposing it, we're not talking about anything else except the reactance, inductive reactance, capacitive reactance in AC circuits. So, what unit is used to measure reactance? We think about resistors and reactance, and we think about ohms. So, that is the unit of measure, not the value. It's the unit of measure. Which of the following causes opposition to the flow of alternating current in a capacitor? We're talking again about alternating current. We're talking about capacitance, just like we were talking about inductance. And you look at these things and at the choices of the answers here, and conductance, nah, reluctance, no, admittance, what are those? Did we ever talk about those? Again, we're talking about reactance. See, this is all simple questions. This is the pool of answers for circuits. These are actual questions and answers. It's not that difficult. Don't get too anxious about it because these are really easy questions to answer. So, how does a capacitor react to AC? When you look at the different questions here, again, we're the capacitor as far as AC is concerned. If you remember how it acts as far as whether the reactance increases or decreases, it's how whatever frequency is applied to it, whether the frequency is increased or decreases. But your simple answer here is A. As the frequency of the applied AC increases, the reactance decreases. In other words, the opposition of the frequency or the alternating current going through it actually decreases as the frequency increases. How does an inductor react to the AC? Well, it's pretty much opposite of what the capacitance does. And if you look at this, um, I don't say really the opposite in the strictest sense because there is the similarities in which in an inductance, as the frequency increases, so does the reactance. It doesn't decrease. In a a capacitor, as the frequency increases, the reactance decreases. In an inductor, as the frequency increases, the reactance increases. So there you go. What is impedance? Okay. When you look at these answers here, there's only one logical answer that you can actually come up with this. Again, the impedance is an opposition to something. So it happens to be the opposition to the flow of current in an AC circuit. That's what your impedance is. So what unit is used to measure impedance? Again, just like reactance, just like resistance, you're using ohm. Ohm, ohm. I don't mean sitting around, going ohm, ohm, ohm. Let me see if I have that image up here. Da 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 da. Ah, no, I don't. Okay. I had a little cartoon here that I wanted to show, but for some reason, I can't find it right now. Nope, 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 nope. Don't know where it is. All right. No biggie. Moving right along. Which of the following describes one method of impedance matching between two AC circuits? Remember, we were talking a little bit about the inductive and the capacitive networks. In other words, as you look at this, and when I mention that, you automatically should, in your mind, focus on the letters LC. So you're going to insert an LC network between the two circuits to give you an impedance matching between those two circuits. What is one reason to use an impedance matching transformer? Very careful with this. You want impedance matching for a very specific reason, and it's not to minimize your transmitter power output, and it's not to reduce power supply ripple or minimize radiation resistance. When you have an impedance matching, you're maximizing the transfer of power. So if your antenna is impedance matched to your transmitter, you're going to have a maximum transfer of power output to that antenna. Why is impedance matching important? This is, again, just a rehash of the last question that we had. This could be either one of these questions could be on the exam, who knows? But really, again, it's so that the source can deliver maximum power to the load. In this case, your source is your HF transmitter, or any transmitter, as a matter of fact, to the antenna. The load is your antenna. So you want to get maximum power out from the source to the load, from the transmitter to your antenna. Which of the following devices can be used for impedance matching at radio frequencies? Um, again, be careful with this one. As you look at it, you can. There's a lot of them that make sense here, and maybe one that doesn't make sense. But however, the following devices can be used for impedance matching at radio frequencies. You can use a transformer for impedance matching. Okay, it's not a transformer just for a power circuit or anything like that. You can also use a pi network. And also, the length of a transmission line can help with the impedance matching of your antenna. The G5RV comes to mind because there is a specific length of twin lead or ladder line, or, however how you want to call it, to the antenna itself. So, really, all of these choices are correct as far as being able to do impedance matching for radio frequencies. And a transformer, a balun, in other words, is a type of transformer for RF signals. So what happens when the impedance of an electrical load is equal to the output impedance of the power source, assuming both impedances are resistive? We're talking about a specific resistive load here. Um, and if the impedance of an electrical load is equal to the output impedance of the power source, assuming both impedances are resistive, and that's again, think about this, your power source being your transmitter and your electrical load being your antenna. That way, kind of reverting back to some previous questions here, this is so the source can deliver maximum power to the load. Again, it's just a different way that they've worded this question. Um, just kind of bear that in mind. So, what should be the impedance of a low pass filter as compared to the impedance of the transmission line into which it is inserted? Okay. Um, the low pass filter, you got to think about the HF bands as being um, the lower RF spectrum, if, as it were. And this is why you would, if you're troubleshooting interference on a TV, let's say, for instance, TV frequencies, of course, are a lot higher than your HF frequencies. Um, and you could put a high pass filter on the back of the TV so that only those frequencies that the TV is designed to receive will pass through that high pass filter to the TV, namely the TV station transmissions, and block anything that is of lower frequency, namely your HF transmissions. Conversely, a low pass filter is going to pass the frequencies of your HF station, and it would knock out any spurious emissions that might occur at higher frequencies. So that would interfere with, say, an FM broadcast receiver or your or a TV. So really, the impedance of a low pass filter as compared to the impedance of the transmission line to which is inserted should actually be about the same. So, which of the following is a reason not to use wire wound resistors in an RF circuit? You got to remember this. You don't want to use these in an RF circuit because they are wound, and in essence, in an RF circuit, they act like inductors and could affect how your signal is routed through your radio. So the answer to this is B. The resistor's inductance could make circuit performance unpredictable. Which of the following is an advantage of ceramic capacitors as compared to other types of capacitance? Remember that those little capacitors, ceramic capacitors, are what make your HF rig a little bit more affordable. So they comparatively are of a lower cost. The advantage of using a ferrite core, ferrite core toroidal inductor. I'll get it out here. So, what is the advantage of using one of these? Remember that uh, an inductor creates a magnetic field around it. But in some instances, in some circuits, you don't want that magnetic field to interfere with other components or other circuits within your radio. Um, but let's kind of look at these a little bit. So, large values of inductance can be obtained with a ferrite core toroidal inductor. The magnetic properties of the core may be optimized for a specific range of frequencies. That core is adjustable so that you can kind of fine tune the internal aspects of that circuit. And it also uh, performs the function of containing the magnetic field, most of that magnetic field within the core itself. So, in actuality, all these answers are correct. That is an advantage of using a ferrite core toroidal inductor. How should the winding axis of two solenoid inductors be oriented to minimize their mutual inductance? Okay, you want mutual inductance in a transformer in which you want to make sure that you uh, pass whatever comes in to the output as precisely as possible. But however, in solenoid inductors, you don't want them to have mutual inductance. So really you want to put them to right angles of each other. Your answer is C here. What causes a voltage to appear across the secondary winding of a transformer when an AC voltage source is connected across its primary winding? You have, again, we're talking about this inductance, okay? So it's mutual inductance, basically. Those windings are wound pretty much together, and as one AC signal is presented on one winding, it causes a mutual inductance to be imposed on the secondary winding. And again, you also keep in mind that high voltage on the input, low current, low voltage, higher current on the output or the secondary winding. Um, we're probably going to get into that question here pretty soon anyway. Um, that would be a step down, called a step down transformer. High voltage, low current, going to the output to the secondary of low voltage, higher current. That's a step down. Low voltage in, higher current on your primary. You get a higher voltage, lower current on the output or the secondary winding. That's a step up transformer. So, why is the conductor of the primary winding of many voltage step up transformers larger in diameter than the conductor of the secondary winding? Why is the conductor of the primary winding? This is to accommodate really the higher current of the primary. The conductor of the primary winding of many voltage is larger in diameter. We're talking about the diameter of the conductor itself, not how many windings there are, but the conductor itself. Um, so if it's a step up transformer, you're going to have a higher current, lower voltage, higher current, and thus you need a higher or a heavier uh, weight type conductor, larger diameter conductor. So, what is the RMS voltage across a 500 turn secondary winding in a transformer if the 2,250 turn primary is connected to 120 volt AC? This is should be relatively easy to come up with. And really, what you're going to do is kind of memorize this. You have a secondary winding um, that's smaller than the primary. You have more windings on the primary, less windings on the secondary. It's therefore considered to be a step down transformer. You apply 120 volts AC to it, and you can go through all this uh, calculation if you want to get the square root of the values and everything, but just memorize 26.7 volts for crying out loud. That's all you got to do. What happens if you reverse the primary and secondary windings of a 4-to-1 voltage step down transformer? Um, the secondary voltage, when you look at it, okay, you're reversing the primary and secondary windings of a 4-to-1 step down transformer. So if you put voltage in on the secondary, which now becomes the primary, um, and you get basically you get 4 times the primary voltage. So the number of windings, the higher value windings on the secondary, which has now become the primary, is 4 times uh, larger. What is the turns ratio of a transformer used to match an audio amplifier having a 600 ohm output impedance to a speaker having a 4 ohm impedance? So you need a certain amount of turns ratio. And this is very simple to do. If you pretty much divide 4 into 600, you really come up to a 12.2 to 1 uh, turns ratio. So you have 600 ohms going in to one side, 400 ohms on the outside if it's a 12.2 to 1, 12 to 1 ratio transformer. All right, that does end the session for this evening. We're at 8:45. Didn't do too bad on this. Again, tomorrow night, the next session is going to be session number 9. And session number 9 has quite a number of slides in it. I think we'll be able to get through it. It shouldn't be too difficult to understand, but we're going to cover the topic of HF antennas in session 9. So, again, if you have any questions, to drop me an email. You can send it to Wayne at n3lms.net. And I'll be more than happy to try to answer your questions, or we can get into a discussion of something that you may not necessarily understand completely, and we'll go from there. So thanks for joining me. That's it for this session. Take care.